Well, let's talk about how you go about approaching these stoichiometry problems. So whenever you see a question that gives you information about multiple chemicals, and more specifically, it asks how much of one chemical and gives you an amount of a different chemical, you know that's stoichiometry. And stoichiometry means you need a balanced equation. So part of that is you need to know some chemical formulas. You need to know that ammonia is NH3. You need to know that nitrogen, pure nitrogen, means nitrogen gas. It's a diatomic element, so it's N2. And hydrogen, likewise, as a diatomic element, is H2. So it says ammonia can be made. That means ammonia is the product of a reaction. I suppose maybe I'll do it over here just to kind of have it out of the way of where I'm going to be doing my work. So NH3. And then it is made by reacting these two. So this is saying this is made, and these are what you react to make it. So that means hydrogen reacts and nitrogen reacts. So this is the reaction right here. And then you have to balance it, of course. There's two nitrogens. So let's put a 2 right here. That way you have 2 nitrogens, which is great, except now you have 6 hydrogens. So we put a 3 right here. And now it's 6 hydrogens. So 2 nitrogen, 2 nitrogen, 6 hydrogen, 6 hydrogen. Okay, cool. We're good. We're balanced. Now we can do this because, why did I need to balance this? Because the only way to relate two different elements is by using moles, and more specifically the mole ratio from the balanced equation. So it says, what's our given here? That many moles of H2. So 1.40 times 10 to the third moles, and always include your chemical identity. So moles of H2 times, and then what do? We need to go from moles of H2 to an answer of how many moles of NH3, so to moles of H3. Moles of NH3. So that means we're just going from moles of one thing to moles of another. So the conversion factor is going to be just from the balanced equation, because you need moles of H2 on the bottom. That way moles of H2 can cancel moles of H2. And you need moles of NH3 on top, so that you can have moles of NH3 in your answer. So now that you've figured that out, you take this mole-mole ratio comes from the balanced equation. See the H2 right there? There's 3 moles of H2. That coefficient of 3 goes right here. So 3 moles of H2. How much NH3? There's a 2 next to the equation, so you put a 2 next to it here. So we're going to take this number times by 2 divided by 3. So just to show you what that looks like on a calculator, 1.40 times 10 to the third. Okay, 1400 times 2 equals, divided by 3 equals. Now you're going to get that many moles. So it's 933.333 repeating moles of NH3, which we then want to round properly. So remember that you got to look at your Sig Figs. This is infinite Sig Figs, because anything that comes out of here is infinitely correct. It's like 3.000 going on for infinity. So because of that, this does not affect your rounding, this does not affect your rounding, but this does. You're given something with 3 Sig Figs. So since these don't affect anything and you got 3 Sig Figs here, you're going to round your answer to 3 Sig Figs, which is 933 moles of ammonia. Or you could potentially put this in scientific notation, 9.33 times 10 to the second. Either way, that's your answer. So that's how you go do what we call a mole-mole conversion. Now the rest of these all work the same. Make sure that you do your formulas correctly, because obviously if you do the wrong formula for this, you're going to get a wrong balanced equation and then a wrong answer, of course. So given that, the next thing is let's look at a different example, because the other two work just like what you just saw. So let's look at 11.5. What mass is required to react that many grams of methane? So now when we say mass, we're talking grams. So before we had a moles to moles conversion, now we're talking about a grams to grams conversion. But you'll notice it asks about one element and it tells you information about a different one. And that tells you this is stoichiometry. And what does stoichiometry mean? It means you need a balanced equation and a mole-mole conversion. Again, the fact that it gives me information about one thing, one chemical, and asks about a different one means I need a balanced equation and a mole-mole conversion. So let's do that. Oxygen reacting with methane, this is a combustion reaction. Okay, this is seeing if you remember some of your things from way back. So oxygen reacting with methane, and it gives you CH4. And then it says it's a combustion reaction. That is seeing if you remember that whenever you combust something, that means burning it. Anything containing carbon will produce CO2 as a product. Anything containing hydrogen will produce water as a product. So that's a combustion reaction for methane. Now, we need to do a balanced equation so we can do a mole-mole conversion. That way we can get from grams of oxygen to grams of methane. So in order to do that, we need to, well, look at this. Okay, so 1 carbon, 4 hydrogen, 2 hydrogen. Okay, let's make that 4 hydrogen. And then how many oxygens? We have 2 oxygens plus 2 more is a total of 4. So if we put a 2 here, we now have 4 oxygens. So that's 4 oxygen, 2, and 2 more is 4. So 4 oxygen, we're good. And then carbon, 1 carbon, 4 hydrogen, 4 hydrogen. Okay, so that's good. Now, the next thing we're going to do is then look at how we're going to do this. We're going to have to go from grams of O2 to moles of O2 to moles of CH4 to grams of CH4. That's just how these work. If you give a mass of one thing, if you give a mass of one thing and ask for mass of another, you've got to do, and I'm sorry, I totally messed up the order of that. Grams of CH4 to moles of CH4 to moles of O2 to grams of O2. Sorry, I got that backwards because you're given methane and you need to figure out oxygen. So this is the process. You got to go through grams to moles to grams. And again, each of these says CH4, I swear. All right, now here's how that's actually going to look. If we're going to go from grams to moles, we need the molar mass of methane. If we're going to go from grams to moles for oxygen, we need to know the molar mass of oxygen. So what is the molar mass of oxygen? We'll do that first because it's easy. Oxygen, when you round it to the hundredths place, is 15.9, okay, 16.00. So oxygen is 16.00, and you times it by 2 because it's O2. So that's 32.00 grams per mole for O2. Now what about CH4? That's 1 carbon, that's 12.01, because you take carbon around to the hundredths place, 12.01. And then for 4 hydrogens, you got to take 1.007. Is that in focus? Let me try. There we go, it's in focus. 1.008 times 4. So plus 4 times 1.008 grams per mole equals, I'll do that on the calculator, 12.01 plus 4 times 1.008, and that's that right there. We round to the hundredths place, don't forget. So it's 16.04. So 16.04 grams per mole CH4. All right, now for the actual calculation itself, here's how we got to do it. We're going to write our given, 45.63 grams of CH4. And then we're going to set up our conversion factors. I'll do it Lynch style. You could also do this whole gain style with like your given and then times and then a conversion factor and then times and then a conversion factor and whatever. But if we're going to do this, then we're going to have to put grams of CH4 on the bottom and moles of CH4 on top. That way grams of CH4 can cancel grams of CH4. And then we're going to do moles of CH4 on the bottom again. That way it doesn't wind up in the final answer. And then we're going to go from grams of CH4 to moles of CH4. That's what's here. Now from moles of CH4 to moles of O2. That's what's happening there. And then our final conversion will be from moles of O2 to grams of O2. That's what this is right here. So grams of CH4 to moles of CH4, moles of CH4 to moles of O2, moles of O2 to grams of O2. And that'll give us an answer in terms of grams of O2. Now, how's that going to look? For grams to mole conversions, use the molar mass. So 1 mole of CH4 has a mass of 16.04 grams. This mole thing, it comes from the balanced equation. So we have a 2 next to the O2, so we got 2 moles of O2. We got no number next to CH4, so it's just 1 mole of CH4. And then as for moles and grams, 1 mole of O2 has a mass of 32.00 grams of O2. So there we go. Our calculation now is going to be this divided by this times this times this. Let's do it. So 45.63 divided by 16.04. All right, and then times 2, and then times 32. Technically 32.00, but same deal. Now, okay, that's 182.06, 182.06, 48, blah, 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 so on and so forth, grams of O2. But we got to round that for Sig Figs. This is 4 Sig Figs. This is also 4 Sig Figs. Molar masses do count for Sig Figs. This is infinite. A mole-mole ratio is not looked at for significant figures. This is 4 Sig Figs also. Molar masses count for Sig Figs. So 4 Sig Figs is going to be because 4, 4, 4, and infinite. So given that, we need to round to 4 Sig Figs. So our answer is going to be 182.1 grams of O2. And I'll box that to make sure it's clear that that's the final answer. All right, so that's how you go through the process for this. Now 11.5b will go through the same thing except with iron 3 chloride. Now let's do an example for 11-6. It is actually pretty much the same thing, but nonetheless, let's go through it. How much bromine? Don't forget bromine is a diatomic element, so pure bromine is Br2. Reacts with 15.0 grams of zinc. Zinc is not a diatomic element, so it's just Zn to produce zinc bromide. Okay, so here we're seeing if you know your chemical naming. You have to know that zinc is a 2+ ion. Bromine, when you look it up on the periodic table, is a 1- ion. The zinc is one you have to memorize. It's located right here. Remember the +1, +2, +3 pattern? All right, anyway, this is the charges of the two and put them together. Switch the charges, you get this 2 from the zinc goes down to the bromine. This 1 from the bromine goes down to the zinc, meaning you have zinc, 1 zinc, and 2 bromines in the formula. So ZnBr2 is your product. So it says, how much bromine reacts with zinc metal to make zinc bromide? So we're saying Br2 plus Zn produces ZnBr2. Remember we figured out that that's the formula? Well, look at what's nice. 1 zinc, 2 bromine, 2 bromine. It's already pre-balanced. We don't need to do any balancing because it's already balanced. How cool. We're going to do just like we did above. And our strategy is going to go from grams of zinc to moles of zinc to moles of bromine to grams of bromine. Okay, because when we say how much, we mean to say how many grams. All right, now that being what it is, let's go ahead and go through that. Okay, so we're going to go from grams to moles to grams. What are we missing in order to do that? We have the balanced equation, so we can do the moles to moles. But what about grams to moles? We need to look at the molar mass. So for just zinc by itself, the molar mass of zinc is right here, 65.38 grams per mole. So zinc is 65.38 grams per mole. And then bromine, that's 2 times, and then we look up bromine's molar mass, 79.90. Remember, round to the hundredths place. 79.90. So, what is that? 79.90 times 2 equals 159.8. But don't forget, hundredths place. This affects your rounding for molar mass later, or for your answer later on. So make sure molar masses always go to the hundredths place, even if that means adding a 0 onto what your calculator spits out. All right, so hundredths place it is. Now, this is what we need to go from grams to moles to grams. Now for the actual thing, we write down our given, 15.0 grams of zinc, and this time I'll do it whole gain style because you saw the Lynch style up here of making these boxes for the conversions. Now I'll just do it whole gain style with the conversion factors. I'm going to put grams of zinc on the bottom so that grams can cancel grams of zinc. And then I'm going to put moles of zinc on top because we need to go from grams to moles, so from grams to moles. And then the next one will be from moles of zinc again because moles of zinc cancels moles of zinc. to moles of bromine. And then we go from moles of bromine to grams of bromine, because that's our answer, is how many grams of bromine. And we'll get an answer in terms of grams of bromine, because moles of bromine cancel moles of bromine, moles of zinc cancel moles of zinc, grams of zinc cancels grams of zinc, leaving grams of bromine as the unit of the final answer. So before we do that, though, let's fill it in. So grams and moles, what do we do with this? We go here, the molar mass of zinc. 1 mole has a mass of 65.38 grams for zinc. For here, mole-mole ratio, we look at the balanced equation. And for every 1 mole of bromine, there's 1 mole of zinc. All right, so again, because there's no coefficient, we just take a 1 for these. Now, final part here, grams and moles, this is the molar mass right here. So 1 mole of bromine has a mass of 159.80 grams. So we're going to take this, divided by this, and times this. That's basically what it is, because obviously multiplying or dividing by 1 doesn't do anything. So 15.0 times, divided by 65.38 times 159.80 equals 36.66258795 blah 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 grams of bromine. We need to round that. So 3 sig figs, 4 sig figs, infinite sig figs, 5 sig figs. So 3 sig figs it will be. So that's going to be 36.7 grams of bromine will be our answer to this one. Oops, forgot to make that BR2. All right, so that's how you go about doing 11.6a. Let's move on. 11.7a. All right. Sodium hydroxide reacts with carbon dioxide to produce sodium carbonate and water. If that many grams of sodium carbonate are produced, then how many grams of water were made? Okay, so what we're going to do is we're going to go from grams of Na2CO3 to, and oh, by the way, how do I know I'm going to do what we're going to do? I see given information about one chemical, and we're asked about another different chemical. That tells me we need to do a conversion involving moles. It's going to be a balanced equation. It's going to be stoichiometry. So we're going to do a mole-mole conversion, and we're going to be converting 2 moles, and then from moles of one thing to moles of another, which means we're going to need a balanced equation. But before that, let's make a strategy. We're going to take we're given this, the grams of sodium carbonate, and we're going to convert to moles of sodium carbonate, and we're going to convert that to moles of water, which we will then convert to grams of water. That's our strategy. So in order to do that, though, we need to make that, in order to make this happen, we need a balanced equation. So our balanced equation will be sodium hydroxide, that's NaOH, reacts with carbon dioxide. And just to let you know, how do I know that sodium hydroxide is NaOH, aside from just searching for it? Sodium, if you look it up on the periodic table, is a +1 ion, so it's a plus. Hydroxide is a polyatomic ion, it's a -1. So you have 1 sodium and 1 hydroxide for NaOH as the formula. But anyway, sodium hydroxide reacts with carbon dioxide to produce sodium carbonate and water. So we need to balance this equation. Now, the first thing I'm going to do is, like you'll notice, oxygen is in multiple places. So that's complicated. Let's say that for last. So it's going to be hydrogen is only in one place here, one place here. Sodium is one place here, one place here. That's the easiest thing to start with. So let's start with, I'll put a 2 here because that's the 2 sodiums, 2 sodiums. All right. Well, that makes 2 hydrogen. And oh, look, there's 2 hydrogen. So we're good for sodium. We're good for hydrogen. How about the oxygens? We have, this is 2 oxygens plus 2 more is 4. So that's 4 oxygens. Here we have 3 and 4. Oh, so there's 4 oxygens here. So you know, by putting the 2 here, I fixed everything. So that's good. Now it's balanced. That means now the next thing we can do is figure out what is, okay, we can convert from moles of sodium carbonate to moles of water, because you've got this relationship right here. Oh, sorry, this relationship right here. That doesn't finish us up, though, because in order to do from grams to moles, we need molar mass. So the molar mass of Na2CO3, so let's see, Na2CO3, its molar mass is 2 sodium, so that's 22.99. So 2 times 22.99 plus carbon is 12.01 when you round it to the hundredths place, plus 3 oxygens. Oxygen is 16.00 to the hundredths place, so 3 times 16.00 equals 105.99 grams per mole Na2CO3. All right, so that's 1 molar mass. The other one we need to deal with is water. That asks how many grams of water. So water, H2O, that's 2 times 1.008 because water is 1.008 when you round it to the hundredths place, or sorry, the thousandths place. Remember, hydrogen is you round to the thousandths place. So 2 hydrogens, 2 times 1.008 plus oxygen rounds to 16.00. So 1.008 times 2 plus 16, that's going to be 18.02 grams per mole for H2O. Okay, so now we have everything we need. I'm going to write my given 16.9 grams of Na2CO3, and I'm going to set up my multiple conversion factors. So I'm going to put grams of Na2CO3 here, convert that to moles of Na2CO3, and then I'm going to put moles of Na2CO3 here so that I can cancel this up here. This is here so we can cancel with this. So this right here is me doing this from grams to moles of Na2CO3. This is me doing this part, moles of Na2CO3 to moles of H2O. So I'll put moles of H2O here because, again, this Na2CO3 is on bottom, so I can cancel this because moles of Na2CO3 here cancel with moles of Na2CO3 here. Finally, our last conversion step is to go from moles of H2O to grams of H2O because moles of H2O cancels moles of H2O. That way we can get grams of H2O for our answer. So that is why we set it up the way we did. Now let's fill it in. So when you have grams and moles, that's molar mass, the 105.99. So 1 mole has a mass of 105.99 grams of sodium carbonate. Now for the balanced equation, there's a 1, there's no coefficient next to the water, so I put a 1. There's no coefficient next to the sodium carbonate, so I put a 1. Now for water, 1 mole is 18.02 grams, or has a mass of 18.02 grams, according to this right here. So this is the mass of 1 mole of water. So we're going to take this divided by this times this. So 16.9 divided by 105.99 times 18.02. And you get 2.873271063 grams of water, which we need to round properly. 3 Sig Figs, 5 Sig Figs, infinite Sig Figs, 4 Sig Figs. So that means 3 Sig Figs it is. 2.87 grams of water would be your answer for this particular question. Okay.